Okay guys, so here we're going to start working on trig identities. And trig identities are just basically geometric or arithmetic or algebraic proofs or equivalencies between two ideas. There's some identities that we already know that we take for granted. And once we get to know more and more and more of them, we can use those identities as sort of branching off points to maybe prove more complicated or complex relationships between trig ratios or other things for that matter, using these principles of a geometric proof. So some proofs that we already know already is the definition of sine and cos and tan. We also know the Pythagorean Theorem. That one's definitely a geometric identity that relates to sine, cos, and tan and the unit circle. Okay, we also already have relationships for reciprocal trig ratios that we've come to know. Whether we know the cosecant, of course, as being r over y, it's also 1 over sine theta, okay, or 1 over sine. Secant is r over x, okay, or 1 over cos, and then cotangent is x over y, or sort of run over rise, and that's the same thing as 1 over tan, okay? And so what we start to do is we start to use these definitions to start looking at relationships between, for example, secant and cosecant, or cosecant and sine, or cotangent and tan, and then we sub those in to state more equivalencies that exist between different ideas and different trig ratios, okay? Well, the first one that we're going to look at is the quotient identity. We're going to use that to look at how we actually prove things. So the quotient identity is as follows here, okay? So this is obviously something that someone would have come up with and then proved it for all values of theta. Maybe notice this principle or notice these ideas, or by definition knew what they were. Either way, we know that tan theta, the left side of the equation, if it's true, is going to equal the right side of the equation, sine theta over cos theta. And so we have to prove that tan theta is equal to sine theta over cos theta. And the way in which we do that is by adjusting the expression, okay, left side or right side or both, so that we can find an equivalency between the two. In other words, we can make them equal to each other. Okay, and that sometimes takes a little bit of work in order to do. All right, so what we do is we start with what we know about tan theta, which is that it's y over x. And really the strategy, one of the big strategies we want to use, other than making the left side equal to the right side when we do these proofs, is that we want to substitute in for the more complicated expression and simplify it down so we can get it to look like the simpler expression. Well, the simpler expression I would say is tan versus sine theta over cos theta, or y over x versus, you know, the definition of sine over the definition of cos. In fact, when I plug it in there, y over r over x over r, and I take the numerator, y over r, and excuse me, and I divide it by x over r. Remember that I multiply by the reciprocal fraction, okay? And I get basically y over r over xr, and the r's cancel out. The r's are both the radius of the same circle, and so we're left with y over x. Now what's y over x? That's tan x, or it's the same thing as the left side. So we say that the left side is equal to the right side, and that basically it has been proven. Okay? Now we are going to want to keep that quotient identity around, okay? That sine theta is equal to, sine theta over cos theta is equal to tan theta. We want to have that in our back pocket. And there's variations on the theme. Okay, if we isolate for cos theta is going to equal sine theta over tan theta. And if we isolate for sine, sine theta is going to equal cos theta times tan theta. So it's good to have this kind of in your back pocket or off to the side when you're doing these questions. And here I have it written here as well. But I want to have it on this sheet of paper so that when we're doing a proof, we can come and see it when we need to see it. Well, whenever you think of tan, think of this, okay? Whenever you think of cosecant, secant, or cotangent, think of the primary trig ratios that they equal. 1 over sine theta, 1 over cos theta, and 1 over tan theta, or reciprocal trig ratios. That's where they get their name from. So that's another important identity. Another big one that we're supposed to be looking at and understanding is the Pythagorean identity. That if I take the sine theta and I square it, and I take the cos of theta and I square it, that's going to equal 1. Okay? Now, when they write the squared, they don't put the squared up in the angle. they put the squared in between the ratio to say that the entire ratio is going to be squared. So as a result, you're going to look at sine squared as the same thing as sine squared theta. So sine squared theta and sine theta squared is exactly the same thing. Cos squared theta is the same thing as cos theta squared. Let me just check the time. Okay, I'm good for time. All right, so what I'm going to do is take their basic definitions of sine and cos. I'm obviously going to, because I'm going to prove that left side is equal to the right side, my right side is 1, which is very, very simple. So I'm going to leave the 1 alone, and I'm going to take sine theta and cos theta and plug in for those. Well, sine theta is y over r. Cos theta is x over r. I square the y, I square the r, I get y squared over r squared. I square the x, I square the r squared, I get x squared over r squared. Common denominator here. Okay, you have to have a common denominator in order to add things. We've got to remember all of our basics. Okay, all of our algebraic basics and bedmass basics in order to do this. Y squared plus x squared. Now, y squared plus x squared is the same thing as the Pythagorean Theorem. Y squared plus x squared is equal to r squared. So I take y squared plus x squared plus y squared equals r squared, and I plug in an r squared in for this. And I get r squared over r squared, which is 1, and the left side is equal to the right side, and so I have proven it. Okay, and that's called a Pythagorean identity. And that's another one we want to have in our back pocket. Sine squared theta plus cos squared theta is equal to 1. If you do any isolating, you can go 1 minus cos squared theta is equal to sine squared theta, and 1 minus sine squared theta is equal to cos squared theta. You can even factor this difference of squares and get 1 minus cos theta, 1 plus cos theta, perfect square, 1, 1, cos, plus, minus, or minus plus. Okay, and the same idea here. So whenever you think of squares, think of this identity. Whenever you think of tans, think of this identity. Whenever you see these, think of this identity, or these identities. Okay? So we're going to use those to start solving some. Now here's some pro tips. Okay, things that will help you out in general as you're going along. Okay, so one strategy is try to work with one side at a time. Okay, work with the left side or the right side, keep it simple. Okay, if you start working with multiple things, multiple times, okay, then you're going to have that problem. Also, if you only work at one side at a time, you're not going to transfer from the left side to the right side. Don't do that. Make comparisons. Compare the left side with the right side. Okay? Use ratio types. If you got sine and cos on one side and you got sine, cos, and tan on the other side, then you're obviously going to want to substitute for tan so that they're all in sine and cos, so you can have sines and coses left and right. In general, that's a good rule. But if you have a sine and a cos on one side and only a sine on the other side, then make sure you substitute in for the cos so you can get the sine. Remember, these identities are equal to each other. That has already been proven. So as a result, that's already been established. So as a result, all you have to do is prove that it exists. Okay, so keep that idea in mind. Other comparisons that are going to be useful is if the left side has two terms, so look at number of terms, or fractions, for example. If there's two terms on one side and one term on the other, then you know you're going to have to work with the left side and add those fractions together, or add those expressions together to create only one on the other side. Okay, if there's factoring, you may have to expand on one side. If there's brackets on one side of the equation and then expanded versions on the other side of the equation, then you're going to have to expand the brackets to make them look like the left side, or factor the brackets to make them look like the right-hand side. Okay? And you're always going to want to look back at your original left side and right side and compare them back and forth and back and forth. Am I closer? Have I gotten further away? Has I made a bigger mess, or is it starting to simplify? And sometimes you have to trust a few steps down the road that it's going to simplify when it doesn't look like it's going to start with. Okay? All right. Also, if you see a sine squared or a cos squared, think the Pythagorean identity. If you have varying powers of sine theta, cos theta, tan theta, so let's say you have a squared or a cubed, or a squared and a cubed, or a cos and a cos squared and a cos cubed, or a number and a cos cubed, okay, or cos squared, then think about factoring. There's a little aside step where you actually substitute in for the ratio, and then by doing that, you make it look like something that you're used to factoring from the quadratics unit or from the rational expressions unit. factor it, and then put the trig ratio back into it. And that's a little strategy I'll show you for some of these. Okay, so this is the overview of what we're going to go to. Now what I'm going to do is I'm going to tape individual examples as we go through them and explain some strategies as we get there.